a special note of thanks for the great honor you bestowed on me. I really appreciate your generosity and hospitality. I feel like I just moved a little bit further eastward, and I'm in the same family I was when I was in Boston. We have so many common interests and common ideas. Extraordinarily impressed by the quality of the work going on here, and the high level of the students. Very exciting things are going on here, and I must say that I think I learned as much as you did in the last 2 days. I'm supposed to give a talk about a subject that's really at the heart of research these days, and that is, I'll explain why. The broad subject is model validation. How reliable are the models we use in simulation and in mathematical science? And, I'll tell you why this suddenly became important. Promise you can give me a warning when my time is running out. I plan to cover these subjects. I'll give you some background. It'll take 10 minutes or so. And then I'll talk about what I call the canonical problem in predictive science, coarse-graining of molecular models, atomic systems, and why I call it the canonical problem. It has all the nasty complications of every problem in predictive science. Then I'll make an argument as why I like Bayesian calculations, Bayesian model calibration, validation, prediction, and I'll talk about a new algorithm that attempts to address the most complex problems in predictive science, and that is, how do you select a model? How do you know which model is the best? And how do you know a model is valid? So, as background, I'll start with the definition of predictive science. People say, why do you have to have the adjective predictive? Isn't all science predictive? And the answer is no, not all. Science is not predictive. And I've added a qualification when I talk about predictive science. I say it has to do with uncertainty. Predictive science is a scientific discipline concerned with assessing the predictability of mathematical and computational models of modulus, physical events, in the presence of uncertainties. It embraces the process of model selection, calibration, validation, verification, and the use in forecasting features of physical events with quantified uncertainty. Now, those are high-sounding words, but it's important to understand the meaning of each one of them. By models, I mean what we all regard as a model. It's a mathematical construction, usually consisting of equations that are inspired by physical laws, or they may be purely empirical. And they're based on inductive theories which attempt to characterize abstractions of physical reality. What does calibration mean? Calibration is simply to take a model which has parameters and run experiments to fit those parameters to the experimental data. And validation, this is a cheap definition of validation. There are much more careful definitions. A model is valid if it agrees with observations. But one must develop a systematic way to determine if a model agrees with physical observations. Verification I'll not talk about. Verification is how good is the corruption of the model done to implement it on a computer. And physical quantities of interest, the physical features of events are the quantities of interest. It makes no sense to ask the question if a model is good enough unless you tell me why you're going to use the model. What is the goal of the computation? Because a model may be a wonderful representation of one type of physical event, but not physical event, another type of physical. So if someone tells you that I'm building a model to understand the dynamics of the system, or the qualitative features of the physical system, don't believe him, because there's no such thing. A model is not designed to do all the features of the physical system. A model is designed to do very specific features if you want to really determine if that model is valid. And finally, what does that mean? I'm going to explain to you why there's uncertainty in every phase of modeling. And how can you put a number, how can you quantify the level of uncertainty? Well, permit me to go way back to various fundamental ideas that have been around for over 2 millennia. Science, what is science? Science is the activity or enterprise concerned with the systematic acquisition of knowledge. The word science comes from the Latin sensia, to know. And people have been arguing for millennia as to how you acquire knowledge. Believe it or not, Aristotle had it right. And subsequent scientists for the next 1,500 years had a mixture of different beliefs on the subject. Aristotle says you learn by demonstration and reasoning. And what he really meant, it was interpreted back in the 18th century, you acquire knowledge by observation, usually accompanied with instruments, experiments, and you acquire knowledge by theory. Theory is a production of an inductive hypothesis and then pursuing the consequences of those hypotheses. Nowadays, there's a new kid on the block, computational science, modeling and simulation, and the big question is, can you acquire knowledge by modeling and simulation? Well, you can if the models are valid. You can acquire knowledge. There are many, many examples where computer simulation can provide information inaccessible by either theory or experiment. So, at the foundations of these pillars is logic. Logic is the science dealing with formal principles of reasoning. And basically, over the centuries, two basic forms of logic have emerged. Deductive logic, or top-down logic, the process of reasoning from one or more general statements or axioms to reach logical conclusions. And that, of course, is the foundation of mathematics. Mathematics is deductive logic, starting with axioms, determine through logic the consequences of those axioms. That's why mathematics, some people say, is not science. Because science is inductive logic. Inductive logic is bottom-up logic, where you observe a phenomenon and you put forth a hypothesis as to what the causes of that phenomenon were. And inductive logic can be wrong. It admits fallacies. Scientific logic can be wrong. The difference between scientific logic and mathematical logic is permanent and forever and irrefutable. Scientific logic only lasts until you find a contradiction. There is a subject called mathematical science, which is a legitimate word. It's often confused. If you have an inductive hypothesis, and you lay down a hypothesis, and then you explore the consequences of that hypothesis, you're using both inductive and deductive logic. And that's mathematical science. So, if we're going to salvage computational science as a pillar of science, we must be concerned about its predictability. We must be concerned about the truth with which we can predict physical events. Some of you have seen this cartoon before. I think it illustrates what I call the imperfect paths to knowledge. We want knowledge because we're going to do predictions. And how do we get knowledge? Well, I said we have observations, we have theory and mathematical models, and we corrupt the models into computational models to acquire knowledge. In every step, we face uncertainties. The observations are wrong because of experimental error. The all models are wrong. They're imperfect mathematical abstractions of physical events. And of course, when you corrupt it further, you get it on a computer, you commit discretization errors. This area of thought, where you're trying to determine the errors produced by discretization, is called the subject of verification. But the real challenging one is over here, validation. How can you cope with errors in the model, errors in the observations of the physical universe, and acquire knowledge and make predictions? Some of these predictions are life and death predictions. You can predict predictive surgery. Can you predict with accuracy the consequences of the surgical procedure? Can you predict climate? How many think you can predict climate? Nobody. I agree. Many vital programs worldwide rely on making predictions without observations. Nuclear test ban is one. We make predictions about the behavior of systems we cannot test or we cannot observe. So it's fundamentally important that we know how to cope with uncertainties. So now we have Aristotelian logic, deductive logic, is the foundations of mathematics and a fundamental component of theory, theoretical physics and science. How can we cope with uncertainties? Well, this is a subject that's also been debated for a while. How can the logic of the scientific method be extended to include uncertainties? One answer to this question is a theorem. We call it Cox's theorem, presented in 1946 by a physicist named R.T. Cox, in which he tried to take a new look at the theory of probability. Basically, his conclusion, which I've summarized up here, every natural extension of Aristotelian logic with uncertainties is Bayesian. That's a remarkable result. If you really want to look at a beautiful result of deep thinking, look at Cox's paper. Because on the basis of trivial, very innocent-looking desiderata, he called them. Desiderata is Latin for desired things. So it's the hypothesis, it's the axioms in a theorem. And his hypotheses were very simple. I have something I'm going to call propositions. I have a real number associated with every proposition, called its plausibility. And I have an algebra of propositions. It's a Boolean algebra. And he developed a logic of propositions using Boolean algebra. He said, I want this to obey the rules of common sense. To him, common sense meant it did not violate the rules of logic. The standard classical Aristotelian rules of logic not applied to numbers, but applied to propositions. And finally, consistency. If two different methods lead to a conclusion, then they have to lead to the same conclusion. So on the basis of this, he had this remarkable proof, and he said, what happens if you have two propositions and they're both right? Conditioned on prior information facts. This is called a conjunction of two propositions. Both A and B are true. What if they're both true? Conditioned on X. And the answer that he proved is that it's the proposition of A given B times the proposition of B given that both A and X are true. These are probabilities. In this last little rule here, in fact, is Bayes' rule. Bayes' rule. Bayes was, many of you know, Bayes was a Presbyterian preacher back in the 16th century. His father was a preacher. He was a good mathematician. He published a lot of papers. Very often they were anonymous. He would publish a paper and he was too proud to put his name on it, too humble. But nevertheless, he was elected into the Royal Society, and somewhere in the middle of his career, he fell upon this theory, this simple little theory. If you've ever taken a course in probability, it's on page 2. It's a very elementary thing. It's the conditional probability. If you give event or proposition A given B is event B given A times the probability of A over probability of B. Now, this rule had actually been known before Bayes. But Bayes came across it and realized its fundamental importance. As a matter of fact, he was so shocked by it he never published it. It stayed on his desk for a few years. And the reason, I've never seen this in writing, this is my own guess. I think the reason he didn't publish it is he saw in it the existence of God. Because it's cause and effect, or maybe the non-existence of God. It stayed on his desk until he died. And the executor of his will was a guy named Richard Price. Richard Price got the manuscript and published it in the Proceedings of the Royal Society. And I will explain what I meant about the existence of God in just a second. It had virtually no impact on science for 200 years. I mean, there were a few people using Bayesian methods in statistics, but by far, statistics was dominated by the frequentist approach up until around the 1970s and 1980s, when the computer, the digital computer came along. Even before that, it was actually used in the 40s and 50s to some extent. But when the digital computer came along and powerful sampling methods were suddenly produced, Markov chain Monte Carlo methods and metropolis Hastings methods and so forth, and implement Bayes' theorem, then the whole field of statistics exploded. And many results that could not have been studied using classical statistics suddenly became in reach. So, I'm going to digress a minute. Oh, I forgot one thing. There's been a huge debate about Cox's theory. Halpern and the computer scientist published this paper in what year was it? 1999. He said he found a counterexample. Cox's theorem was wrong. Then a little while later he says, oh no, I didn't understand the theorem. It was right after all. And then several papers came forth explaining Cox's theorem. The best paper of all, beautiful written paper, is this one by Kevin Van Horn, which is a detailed, deep study of every axiom and step in the theorem. It takes about 15 or 20 pages to prove the theorem. And then, of course, the famous book by Edward T. James, Probability Theory, The Logic of Science, is based on Cox's theorem. And many others, A Trivial Proof, The Theory That Would Not Die by Sharon McGraney. Then a couple of papers, Friedman and others, and Owadi and others said, oh, well, Bayes' theorem doesn't work sometimes. Sometimes Bayes' theorem doesn't converge, and I'll explain what converges mean. And then that was refuted in a series of papers by Klein and Enderlin, showing that under the right conditions, Bayes' theorem will work in the most weirdest and unusual cases, if you can imagine. I'm going to explain what the words will work means subsequently. Okay, now let's get the application. I call this a canonical problem in predictive science. Coarse-Grained models of atomistic systems. One example that I tackled 7 or 8 years ago was nanomanufacturing, where you're stamping out semiconductors, and the dimensions of these semiconductors Well, they were back then 70 nanometers, now they're down to 10, 11 nanometers. So these things are down at the almost atomistic level. They're actually manufactured semiconductor devices. Well, if you take one of these flanges in this device, then these are polymer flanges, and they stamp out units of that thickness, and those units are semiconductors. If you take a 30 nanometer cube, that's around 600 atoms, and you take, each has 600 wide, and then you take that cube times 3 degrees of freedom per atom, you can quickly see that models based on atomistic structures very quickly get out of here. If you take such a model that has 650 million degrees of freedom and you march it 150,000 time steps, you better have an exascale computer on that. So what's been going on for 40 years, this goes back to the 40s, is that responsible scientists lump all these things together. They aggregate atoms into molecules. So instead of having 648 million degrees of freedom, they may have 24,000 degrees of freedom. So these are molecules, or superatoms, in which atoms have been combined, and now you've reduced the number of degrees of freedom. So at least 10 times this last 2 days I've heard about reduced methods. This is the grandmother and the grandfather of all reduced methods. You reduce the number of atoms into molecules. Now, and then what do? Well, you apply Newton's laws. Take the Hamiltonian, you say that the momentum is mass times velocity, and you derive a set of equations and you integrate. Now, you know it's much more complicated than that. You have numerical methods for integration. You have other conditions like you want to keep the temperature constant, you must add conditions to the equation and so forth. But basically, this is classical mechanics. You have a point with a mass, it's moving, and you're tracing the motion of its motion by integrating a set of equations. Now, the most complicated part of these models is what is the potential energy? And here's one example, it's a very common one. This is an example where the potential energy has covalent bonds, it's at angle bonds, it has dihedral bonds, torsional bonds, it has non-local bonds. This is the famous Leonard-Jones bonds. It has Coulomb terms, Coulomb charges, and so forth. Models such as this are found in the standard molecular dynamics codes. And there's several of them, and I know, having talked to people here, some of them are in use at AICES. There's Bromax, there's LAMPS, there's CHARM, there's AMBER. All of these are hardened codes used worldwide for chemistry and molecular dynamics. And some people back in the 90s took the trouble of using X-ray crystallography and quantum mechanics to get very sharp values, at least that's what they say, for these parameters. So you have a set of parameters, I call it theta, and these are all the parameters of this model, and you must know those parameters if you want to follow the dynamics of the system. Well, stop and think a minute. That's close to impossible. First of all, if you give me a set of atoms, there are many, many, many different ways to aggregate the atoms. You just take that little chain there of carbon atoms and hydrogen atoms. I can have 2 B's per ball, two atoms per B, 4, 6, or whatever. So each choice of an aggregation is a different model. So for a finite number of atoms, I may have a very large number of possible models, but that's just a half of it. If you take any one of these models, you don't know the potential. For any one of those models, you can have many different possible parameters to describe the model. So for one of those models, I may have n different So I'm about to make a prediction using an atomistic code. I don't know how to aggregate atoms. If I knew how to aggregate atoms, I don't know the model. What a more uncertain position could I be? And oh, by the way, the date, how do I know the date? Well, let's suppose that the all-atom model was perfect, it was the truth. Even then, it's not deterministic. The properties of the all-atom model in all of these codes are generally determined by a probability density function of some kind. Say, a Boltzmann distribution, which has to be sampled to determine properties of the all-atom model. So I have uncertainties in data, uncertainties in the model selection, uncertainties in the parameter, and I'm trying to make an argument that I'm going to predict something with quantified certainty. So this is a challenging field, and I can tell you, I'm going to give you some answers, but there would be people working on this subject for many decades. There's plenty of work to do. So where do we stand? Well, imagine you're somewhere in the physical universe, and you sample a reality. For example, you're on an asteroid flying past the Earth, and you want the temperature on a mountain in the asteroid. That's a physical reality. So you have some instrument, thermometer, for example, and you try to measure this reality. Well, I'm sorry, you will never measure reality. There's no instrument known in any subject that measures reality with infinite accuracy. There'll always be error. So when you're tabulating the data, this is, science is observation and theory. When you're doing observations, that's reality. When you're tabulating data, you always have an error. I've assumed it's added, it may not be added. So you have experimental error. Now, the inductive part, the mathematical model, the theory. You have some abstract mathematical equation applied in a certain domain, a scenario, with a model who has parameters you don't know. And let's suppose for that parameter, and for that scenario, you solve it. You solve the model and you get an answer. And now you take this solution and you apply it to this point in the physical universe, and you get the model prediction of that event. And when you compare it with reality, it's wrong. All models are wrong. So you have two kinds of inadequacy before you even get started. You have experimental error, and you have model inadequacy, the modeling error, so-called model form error, or model bias. This is a pretty tough problem. I'm not sure what the model is. We get data, we know the data's wrong. We try to use the model to estimate reality, we know that's wrong. So we're in a sinking ship. There's not much to do. And that's the end of my lecture. Thank you very much. Well, remember Cox's theory. Cox said that every Aristotelian extension of Aristotelian logic with uncertainties is basic. So let's go back to Mr. Base. By the way, the great proponent of Bayes is this guy here, E.T. James. He was a real character. He was a physicist. He wrote this monumental book called Probability Theory, the Logic of Science. It's a lot of fun to read. But he has many, many quotes like this, and I like this one, so I'll start this with. The essence of honesty and objectivity demands that we take into account all of the evidence we have, and not just some arbitrarily chosen subset of it. And that is a principle that is constantly violated by people who try to determine the validity of a model. they look at some small piece of the model and validate it, and they ignore all the other imperfections in the model. Here it is again. That's Bayes. In science and statistics, we mainly replace, we look at the special case where the probability measures are absolutely continuous and are characterized by probability densities, and that's the cases I will look at. In that case, Bayes' theorem takes this form for models. You have a vector y of observational data. Remember, you can never get it exact. You record the data as best you can see it, but it's wrong because your experimental instruments are imperfect. And you have a bunch of parameters. And the essence of Bayesian statistics is that you know something, you have prior information. So we presume you have prior information on the parameters. And then if you go down and you say the total error, the modeling error plus experimental error, if you knew the probability density of the sum, a little arithmetic says the sum is the difference between the data and the prediction of the model. This conditional probability is called the likelihood function. It's the likelihood. And I'll come back to that subsequently. And you put all of this in the Bayes' formula, and it spits out the posterior. And Bayes looked at that and saw something most people hadn't seen before. He said, wait a minute. You mean I start with this knowledge, I introduce a model, and I have a new knowledge. I know something new about the parameters. I've learned something. And the answer is yes, that's what you do. You've learned something. So, this was a remarkable observation, and it scared him, I think. Depending upon what hypotheses you introduce to get the likelihood, it will give you something beyond your current knowledge. It's called Bayesian learning. To apply this to the problem of model validation, I advocate using what's called the prediction pyramid. You imagine that you have a set of scenarios, beginning with what I call the calibration scenario. So you have a very complex physical system, and you break the system up into building blocks, small components, and you do individual experiments on the components with a certain set of data. And then you begin putting the components together into subsystems. Those are called the validation scenarios. And there's a new set of data for the subsystem. And you continue to do this until you run out of money. You continue to do this until you can no longer increase the sophistication of the system, and you roll the dice. You hope that you have enough information at this level to make the prediction and to compute the QOI. So you have scenarios, calibration, validation, prediction. You have observations, calibration, validation, and prediction. Some people said, why do you call it a pyramid? What's on the other side? The other side that's never seen is reality. You never see reality. For any of these. It's really depressing for a while until you get used to it. To realize that science is so subjective. Science is very subjective. It's not an objective endeavor. It's a very subjective endeavor. You cope with uncertainties all the way. It's okay if you learn how to cope with uncertainties. You can live with it and still do science. So we start up here with a prior. You plug it in here and you get a posterior for the calibration. Here's an actual calculation. The red one was the prior probability distribution for some parameters. The calibration was an improvement, and then for the new set of data, you improved it further with the validation. Improvement means you sharpen the probability distribution. You reduce the variance. So for example, back to my canonical example, if you had this polymer in a manufacturing cube of it out, you could explore this cube and put my quantity of interest, my prediction would be, let's say, something like the free energy of this cube, or the total potential energy of the cube, or maybe some mechanical properties of the cube. And you pull out representative polymer chains, and these are going to be my validation scenarios, and you break those validation chains into little subchains, these little building blocks, and now you perform experiments on these little building blocks, and you determine the parameters for those building blocks. And then you put the building blocks back together, into more complex chains. You compute the potential energy or the free energy of these chains, and you begin to gain confidence. Because now you've got more information. The Bayesian method says if you supply more data, you ought to increase your understanding of the system and your evaluation of the parameters. So let's go through this business. You need a prior, you need a likelihood, you need the denominator. This denominator is called the evidence. You put them all together, and you integrate, and you come out with a posterior. And the posterior is the answer. Posterior gives you the most accurate information you have with the parameters. They haven't solved the problem yet. You just have the right parameters, or the best parameters. Now you must solve the stochastic system for those parameters. I will show you some solutions, but I'm not going to go into methods for solving them. Generally, I use Monte Carlo methods. You just sample the parameters enough time, and for each sample, propagate the solution into the future. Okay, what is the likelihood? According to R.A. Fisher, a great statistician, who was a frequentist, he was not a Bayesian guy, but he said that the likelihood that any parameter should have any assigned value is proportional to the probability that if this were true, the totality of all observations should be observed. Anyone know what I just said? What he was trying to say is that if you give me a parameter, for that parameter, the likelihood will give you the probability that the data is right. Okay? The likelihood that the data is right. Now, if you have independent and identically distributed samples, the likelihood can be broken up into a likelihood for each sample as the product of the likelihood. And people don't like to work with products. If you take the logarithm on both sides, you get the sum of the logs is the log of the sum, log of the products. And the reason people like to work with log likelihoods, first of all, you reduce the complexity. But the log likelihood and the likelihood have the same maximum. The maximum of this function is the same as the maximum of this one. So, if you look at the maximum, this is a little theorem. I can prove it in about 5 lines. It's rather trivial. And if you take the likelihood for given data, and you ask, what is the parameter that maximizes a likelihood? And if G of Y is the probability distribution for the true distribution, that's the probability distribution that as close as you can tell is the observational data, then that same maximum minimizes this funny looking integral. This integral is called a Kullback-Leibler divergence. It's the integral of G log G over the likelihood. And it's going to pop up over and over and over again. It is not created for a mathematical purpose. It's an unavoidable property of these systems. It's not a metric, it's not symmetric, but it's an unavoidable method to compare probabilities. The DKL distance. Prior. How do I get to prior? The uniform prior, which is just an interval, is the maximum ignorance. nothing about something, but you know extreme bounds. That's called a uniform prior, and it's better than nothing, because if you get data, you're going to improve it. But there was a guy named Claude Shannon. Many of you, I know some of you who discussed Claude. Claude was a genius. He worked for Bell Labs, and he invented information theory. He had his consultant, John von Neumann, and they were working in the 40s on how do you quantify information, and how do you quantify uncertainty. And Shannon, in a theorem very similar to Cox's, he had a minimum number of desiderata, and he derived Shannon's theorem, which says that the only function, we seek a logical measure of the amount of uncertainty in a probability. The only function satisfies at least desiderata is the so-called information entropy. So if you have a discrete probability, it's minus the sum of pi log pi, or the integral of pi log p for a continuous distribution. And moreover, the actual probability maximizes the entropy. It's called Shannon's principle of maximum entropy. By the way, if you have two probability distribution functions, the distance between them is our old friend we just saw in the last slide. It's the DKL measure, the integral of P log P over Q. It's also called the relative entropy. If you expand this, you get it's the entropy of P minus the entropy of P plus this cross term, that's the cross entropy between two distributions. Now, see, I'm running out of time, so I better accelerate here. The beautiful thing that James did this in 1965. He took Shannon's theory and he showed how to compute priors. If you have any little bit of information on the parameters, and you maximize the probability subject to constraints, you get the priors. It's tremendous help. If you have a prior, if you have prior information, it accelerates tremendously the whole process. So for example, if you know the mean, and you maximize this subject to the constraints that you knew the mean, you get sort of this exponential probability. If you know the mean and the variance, you get Gaussian, and so forth. I've got a couple of graduate students who really become experts in this. You can give them a very complicated looking potential function, and they can play with it and play with it. Just the data, it's independent of the problem, it's independent of the data. They give you a prior. The prior works. Now, so remember the formula. I got the prior times the likelihood. What's in the denominator? The denominator is called the evidence. And for many, many years, people said, oh, who cares? The evidence is not important. It's just a normalization factor. The evidence is the denominator, and you need to calculate the evidence to make the integral of the probabilities 1. Turns out that's a big oversight. Turns out that all the meat is in that denominator. If you take the same old basis theorem and you recognize that now I have a set of models, I have n models in the class, and I rewrite basis theorem recognizing that I had more information I didn't tell you about. I had the information that I had m models, and for each model I had the parameters. So you rewrite basis theorem, recognizing priors as the model and the set, and you come up with the marginalization of the numerator is called the model evidence. If you have m models, they're exactly m of these. If you do basis theorem again, a second time, for the finite dimensional system, you get these things called the posterior model plausibility. It means you give me data, you give me a set of models. For each model I can compute their plausibility, and the sum is 1. And the model with a plausibility closer to 1 is the most plausible model. I find that absolutely astonishing. I spent my life as a student being told, oh, you can't, it takes an expert to pick a model. You use your judgment. You get the feel for many years, you know what the right models are. There's no mathematical way to pick a model. Wrong. Compute the model plausibilities. learned bits and pieces of this in books they did in the 1980s. There's a chapter on it in James, but not so sophisticated. Beck at Caltech has made an industry out of this, and it's an extremely important tool. And so, I still have the perplexing problem of too many parameters. Even in my nano manufacturing application, simplest case I have 150 parameters. But I know from past experience, not all of these parameters are going to affect the answers. So I can ask, for the output of the model, which parameters are important and which are not. Well, there's a couple of books on this subject. Sartelli has written 2 books, and basically they're rather crude methods. These are not deep methods. Matter of fact, my student coded this and had results in 2-3 hours. So it's not a week's work. But you can take an output function. Y is an output function. For example, total potential energy. That's a function of the parameters. You tweak the parameters, and you can compute their variance divided by the original variance. Anyway, you get a number, and the number is a sensitivity. It gives you an indication of which parameters can be ignored and which cannot. Here's a calculation done on a polyethylene chain. It had 24 beads. It had covalent bonds, it had angle bonds, it had dihedral bonds, it had Lennard-Jones bonds. We did a sensitivity analysis, and it turns out that dihedrals didn't affect the answer at all. Very little, so we threw them away. So you went from, I forget, you went from 10 parameters down to 6. Tremendous difference. Now we better check it. Does it work? I'm going to have to flip through. And it does work. The blue probability distribution is including dihedrals, and the dotted one is out, and you see they're virtually the same. The DKL distance between these is essentially 0. Okay, now, how do I collect all of these things into one algorithm that it's the most plausible model, determines the parameters, solves the problem of model inadequacy, and gives me a predictive model. Okay, that's what I call OPAL, Occam plausibility algorithm. I know everyone's heard of Occam's razor, right? Occam was a 13th century friar. A lot of these things go back centuries, right? And Occam's razor I used to wonder, why did he call it a razor? Because you shave off assumptions. Occam's razor said, among all competing theories that lead to the same prediction, the one that relies on the fewest assumptions is best. Put it in simple form, Occam said, always use the simplest model. A lot of people, Einstein said, use the simplest model, but nothing simpler. The problem is no, this is not a scientific principle. Because no one knows what simple means. Right? So you have to manufacture your own definition of simple. And to us, simple is a number of parameters. Although I get very complicated models with only 1 or 2 parameters, I'm going to take that as a definition. So how do we choose a model that adheres to this principle? This is a polyethylene cube. I forget how many atoms, half a billion atoms. I want to compute some property. I want to compute its potential energy myself. This is its coarse-grained approximation. And here are my scenarios. This is a cube, that's scenario 2. This is a collection of chains, that's scenario 1. And this is one polymer chain, that's going to be my calibration scenario. So, I start this process, identify a set of models. See, I have the molecular structure for the calibration, and I know from my table all possible parameters I can put in the model. So I do a sensitivity analysis, and I discard all the models, all the parameters, which do not affect the output beyond a certain limit. I then do the open step. I choose the models with the lowest number of parameters. I call those the open categories. And then I calibrate the model. And then I do, among the models in each category, I pick the ones that are most plausible. So now I've eliminated insensitive models and implausible models. And now I do the validation, and I check with the observation, is it close enough for my purposes, and if it is, the model's valid. If it's not, I start over with a new Occam category. So I start with this calibration experiment. I partition this into parameters. These are models of 2, 4, 6, 8, 10 parameters. I do the sensitivity analysis. I find that some of them don't work at all, not important at all. I reduce the 15 models down to 7 models. Their parameters are 2, 4, and 6. Two parameters, 4 parameters, and 6 parameters. I start with the lowest, which is, according to Occam, the simplest. That's these with 4 parameters. I do the plausibility. So I've got category 1, category 2, and category 3. So now I do the plausibility calculations. This is not an easy calculation. I have to use Markov chain Monte Carlo to evaluate the product of these density functions and then compute the interval. When I'm done, I find that only one model is plausible. 3 have plausibilities close to 0, not exactly 0, but 10 to the minus 40. So that's the most plausible. And now I look at the observation data, and I have to have a metric to determine if I will accept the accuracy of the model. I can't tell you how many people don't use that step. If you're going to determine a model validity of a model, you have to tell me what your tolerances are. And don't tell me after you solve the problem. Tell me before you solve the problem what your tolerances are. And if the tolerances are met, you can declare the model valid. Now, a real stickler would say you never declare a model valid. You declare it possibly not invalid. Because if you get more data, or you change the quantity of interest, it can become invalid. So here's 2 possible metrics. One is the DKL. You just say, I'm going to take as a tolerance 15% of the mean, of the order of magnitude of the ensemble average of the internal energy for each parameter. And another is a expected value of these functions. And I'll give it a tolerance of 10% of the quantity of interest. And when I do, I found that the model works. Both of these models are not invalid. And that's the prediction they give of the total energy. But what if I change the tolerance? What if I reduce the tolerance from 0.15 to 0.06? Then this model is invalid. I discard the model. I go through the Occam calculation again, plausibility calculation again, and finally I come up with a model that's valid. If all of the models are invalid, you have to go all the way back to the model classes and pick a more sophisticated collection of model classes. This last one that worked was it's called the unit atom model. It's a carbon chain where you discard hydrogen atoms. Okay, and I'm running a little overtime, and no one is screaming yet, so I will spend about 5 minutes and I will close. I will talk about quickly some mathematical issues. This is more philosophy than practical science. statisticians are worried about the consistency of models. If you have a model and you keep supplying more and more data, do you get better answers? And there was a famous theorem by a Russian mathematician, Bernstein, published in 1917, and the famous von Mises, published in 1938, called the Bernstein-von Mises theorem, which says that if the model, if there's something called the truth, there is a parameter. If there's a magic parameter that gives you the true observation, then, and if the model is smooth, that means the likelihood is second derivatives with respect to the parameters that are bounded and invertible, then the Bayes method always works. The more data you give it, the better it works. This is the Bayesian central limit theorem. When it works, it converges. The method converges to a Gaussian with a mean, that's the maximum likelihood, and a covariance, that's the inverse of what's called a Fisher information matrix. It's the second derivative of the likelihood function with respect to the parameters. Now, if the model is no good, if the model is wrong, it's a much, much more difficult problem. And for the last decade, people said Bayes' method didn't work, but in fact it does. Under conditions on the prior and conditions on the model, this is a condition on the prior, this is the measure of a set of balls the prior concentrates on. This is a misspecified non-parametric model. Bayesian methods still work. Under those two conditions, sufficient conditions, they work. It means work, they converge to a magical parameter that's not the maximum likelihood. It, in fact, is the parameter closest to the truth in the DKL measure. So the DKL measure arises as a ghost, once again. It's behind the scenes in the performance of the Bayesian method. And the parameter closest to the true distribution in DKL measure is the limit of the Bayesian method for these non-geometric cases. Now there's some other things I'll only flip through quickly. You can derive a posteriori error estimates for very special cases. And just to show you that it's possible, you can take a bead, you can coarse-grain it into 2 deep, these are atoms, you can coarse-grain it into 2 atoms per bead, 3 atoms per bead, 4 atoms per bead, and so forth. And you can ask, how is the quantity of interest affected as I continually abuse the model? And you find that you can estimate the error with extraordinary accuracy, and that the more you abuse the model, the more beads you get, that's P, the bigger the error is, which is not a surprise. There's some other small things that you can prove. By the way, this is done using method of adjoints for these dynamical systems that govern the molecular dynamic system. A couple of quick theorems and I'm done. It should be of no surprise that, I think I skipped these, yeah. It should be of no surprise that if you have 2 models, P1 and P2, and P1 is the most plausible, then the parameters of that model are closest to the true parameters. Conversely, if they're closer to the truth, the model closest to the truth is the most plausible. These are not very deep theorems. You can prove them arithmetically in a half a page. I will close with a statement that sort of sums up the principal message. The actual science of logic is conversant and present only with things either certain, impossible, or entirely doubtful, none of which, fortunately, we have to reason on. true logic of this world is the calculus of probabilities, which takes into account of the magnitude of the probability, which is